Today we're going to talk about multi-agent systems. We started already in the last couple of lectures. I showed how to do active objects for Flavius Josephus. But today we're going to see how to make real big and correct multi-agent systems. And these are very important. Whenever you make a program that interacts with the real world, it's going to be a multi-agent system. Now, the real world is very concurrent, it's very distributed, and it's very rare that you have sequential programs running in the real world. Okay? So I made an overview here to give you a context. First, I will give you the basic concepts, and then we will apply them to the lift control system, and we will go through the whole methodology. This is actually not so simple to make it really correct. Okay, so we go through all that, and all of this is actually an introduction to next week, when we will talk about an industrial strength multi-agent system called airline. And this is even stronger than what I'm saying here because it also handles failures. So one of the strengths of airline is failure handling, because when you have multi-agents, maybe an agent fails or the cable breaks. It happens a lot. Okay? So a real multi-agent system has to handle failure. The example I give today does not handle failure. You can extend it to handle failure, but I prefer talking about failure in the context of a system that does it really well. Okay? Airline is probably the best system to do failure handling. In fact, airline is kind of a hidden language. It's widely used, but there's not so much media attention, but it survives and it thrives. It is used a lot because it is by far the best language for failure handling in multi-agent system. Okay, so that's introduction. First, a few seconds of pause for the people in Ukraine who are fighting for their freedom and for our freedom too. Okay. So in multi-agents, we're going to program with court objects or active objects, which I'm going to call agents. You can call it concurrent components. So it's extremely concurrent. Agents are sending messages all over the place. Okay, collection of agents that send messages. So if you do it wrong, it's a mess. Okay, you have to be very careful. It's very easy to make this, to hack something up that is really messy. So that's one of the reasons why I want to show you a good way to do it. And we started already with deterministic data flow. We had stream objects, but that was very easy. Because deterministic data flow is deterministic, it's functional. So the multi-agent programming is like functional programming. So deterministic data flow is like a very easy kind of multi-agent with stream objects. So we saw it in the Flavius Josephus with the victims, but we saw many other examples. Now, but it's not enough because it's deterministic. We will often need non-deterministic behavior, and non-deterministic behavior, as we saw, is needed when your program interacts with the real world, because real world things happen anytime. They're not really, they're not very disciplined, and there might be timing constraints, or like in the lift control system, people can be pushing the buttons anytime. Okay, so there's humans involved, or other kinds of machines, cars driving on the roads, whatever. It's all non-deterministic. Things can happen anytime. This makes it a lot harder than deterministic data flow, okay? And so what I'm going to do today is give you kind of a way to do it so that it has a chance of working, okay? The basic principles. So it's very hard because you have interleavings. All the agents are executing at the same time, concurrently, they're independent, and remember we have the interleaving semantics. So basically they're all making steps at any time, and it has to be correct for all of those interleavings, okay? And that's a lot. It's very exponential, so it's really hard. Okay, so I'm saying that over again, it's hard, it's very hard, because a lot of bugs, these systems have a lot of bugs, because people don't really realize how hard it is. But nowadays, we have techniques to do them. We even have verification tools. There's actually trams or metros in Paris that are completely automated. I don't know if you've taken the Orly Vol from between the Antony station and the Orly airport. It's completely automated, and it was completely verified. So they used an approach like this, but even stronger, because they had a software tool that is actually able to look at all the interleavings and guarantee that it's correct. So they actually did a formal verification of this, not just testing, okay? So when you implement something, you test and you verify, okay? Testing means you're running it in all kinds of conditions, but that's not enough, because sometimes you have rare things that happen once every million executions, and you never catch them when you test. So you have to do also verification, okay? So I'm going to talk a little bit about that in the example. But first I want to introduce some formal concepts of multi-agent systems, some formal concepts, basic operation, links, some examples, methodology, and then we go to the example, the lift control system, okay? So a concurrent component is basically, this is the thing that specifies an agent. So it's kind of like a class, okay? Because when you run the concurrent component, when you invoke it, it creates an instance. And that instance is the agent, okay? And so it's possible to have many agents that actually have the same code inside, because they're instances of the same concurrent component. Okay? In our examples, we'll use port objects. In Flavius Josephus, we used active objects, but it's almost the same. Port objects, the specification is done using a function, state transition function, but in active objects, it's made using a class, an object-oriented class. But that actually is very close. There's a very close connection. So we're going to just do port objects. And I'm going to explain again an example we saw before, which is the full adder. Remember we did digital logic example. This was even in a previous course. But digital logic is deterministic data flow. And we have a procedure called full adder with 5 arguments. And this creates a logic circuit. So a running logic circuit which behaves like a full adder. So that's basically a 1-bit adder. 3 input bits and 2 output bits. And they are streams, of course, because the thing is executing in time. You can have many successive inputs. So the input bits are streams, the output bits are streams. This is an example of a component, and I'll show you this example because it shows already this idea of component and instance. Okay? And there's 4 basic operations. So instantiation is creating an instance of a component. You can also build a new component out of other components. So you can have, in the full adder, you have gates inside. And so you have components inside of a bigger component. That's called composition. You can also connect components. And this is the message channels, actually, okay? Who can send messages to whom? And so you can have different kinds of these connections. In deterministic data flow, there are always one source. That means only one agent can send to another agent. It's deterministic. But with port objects, you can have two agents sending to one agent, so it's non-deterministic. Okay? And so I'll show examples of that. And the final one is restriction. If you make a new component out of other components, inside you can have links that are hidden. So it's kind of like lexical scoping, okay? These are restricted and they're inside. So these are the basic formal concepts. Okay, now if you're a theoretician person, you can define a calculus. You can define a language, a formal language that has this. But I'm not going to do that because when we write this program in Oz, we will see very clearly how these concepts are used. Okay? So when you have two agents connected together, they link together. There's a link between two agents. Here's an agent connecting to another agent. So there's a link. And there's different kinds of links. And this is very important, what the kind of link is, because this determines whether it's deterministic or not, and what kind of, whether you can use stream objects or port objects. Okay, so there's different kinds of links. There's one source links, when the source, it's always the same source sending to the destination, or you can have multi-source links, where you can have multiple sources sending to the destination. Okay, so one source here on the left, multiple source or many source. So the client-server example we saw is a multi-source. But all deterministic data flow is always using one source, okay? And then, so that's one distinction. The other distinction is how many messages can you send on this channel? Can you send one message, or you can send a stream of messages? Okay, so that's what's called a one-shot channel, or many-shot channel, one message or many. The one-shot channel is just a data flow variable. It's a variable that you can bind, and once you bind it, it's done. Single assignment. So it's a channel that you can only send one message. So why is that useful? You only send one message. It's very useful for acknowledgements, okay? And it's also, you can guarantee only one message will come there. Because remember, we're in a very complicated world here. The bugs are everywhere. So if we can guarantee things, it's very good. So these one-shot channels are really nice. Whenever you only need to send one message, you don't need a stream, okay? You can just have a single assignment variable is the way to model a one-shot channel. So only one message can be sent. But you can also have many-shot, where you can send many messages. So that's a stream. So that we saw already in the deterministic data flow, okay? But it's more general when you have ports, of course. So a list that can be extended. But in the one source, it's deterministic. Because the destination knows where the message is coming from. There's no choice is done here. No non-deterministic choice. So this is completely functional declarative, okay? Deterministic data flow only has one source links. We saw this already before, okay? Now I'm putting it kind of more general context. Because we're going to multi-agent. The thing we add is many senders, and we saw the concept, port. So this is a named stream, and any thread can send if it knows the name. And all the messages are added to the stream in a non-deterministic way. It depends on the timing, okay? Any source can send a message, and they are added whenever they arrive. So if you execute the same program more than once, the result can be different, huh? This is the weird thing about non-determinism, huh? And multi-agent languages, industrial languages like airline, they will be using only these many source links. I think that's kind of a mistake, because airline does not have one source links, but you can create programming patterns, kind of abstractions that guarantee this, but the language airline only has these many source links, okay? there are always going to be many shots. There are always going to be many messages coming in. It's not very useful to have one message coming in through many possibilities. So one shot, many source is not very much used today, maybe someday, okay? So this is the distinction, okay? And we'll try always to use the most restricted one because of the bugs, okay? So here's an example that we saw before. I'm going to show you again because this shows almost all the concept except many source. Here I have a full adder, and it is created using seven gates. Languages get mixed in my head sometimes. 7 gates here, and this is the circuit diagram. So all the letters here are streams. Whenever I execute, these are components, and G, OR gate, X, OR gate. Whenever I execute one of these, I will create a running gate. So I'm doing composition here. The full adder contains 7 subcomponents. And whenever I execute the full adder procedure, I will create a full adder component which consists of 7 subcomponents, which are running gates. And the identifiers here will be streams, and they're all going to be one source. Okay? The inputs are connected to one output. There's no way to have multiple guys sending messages. So if you do digital logic, like the microprocessors that you see everywhere today, it's all deterministic, okay? The whole microprocessor, billions of gates, there's billions of these gates, are completely deterministic, okay? So the whole thing is deterministic. In fact, when this thing connects with the external world, that's a problem, because that's non-determinism, huh? So that's kind of neat. Let me just give you a picture. So if you have a microprocessor here, this is all deterministic. So you have millions, billions of gates. It does connect to the external world, and these interfaces will be non-deterministic, okay? And that's actually a problem. Those are actually not easy to do. Like external interrupts. That requires a special kind of circuit to handle the non-determinism. Okay, so I'm not going to get into that, but just to say that most digital logic is completely deterministic. Okay? So it's all using deterministic data flow. And so today we're going to go away from that, and we're going to go to non-deterministic multi-agent. Okay? So this shows you all of the concepts, right? Composition, restriction, linking, okay, and the instantiation, all the 4 concepts here. So we're going to keep those concepts, but extend non-determinism. Okay. But we need to do it very carefully. So I'm going to introduce, here's a methodology. So basically this is kind of a discipline that you have to follow if you don't want to have buggy programs. Okay? Designing multi-agent programming is more difficult. Okay, that's an understatement. It's much more difficult than designing sequential programming because of all the interactions that might give different results. And bugs, the bugs can hide, okay? So there are famous examples where people die because of these bugs, okay? I mentioned already in the 1970s, so this is a long time ago, they had these machines in the hospitals for killing tumors by irradiating them. And there was a concurrent program in there, and there's a keyboard, but they didn't verify them, okay? And so when the technician was typing on the keyboard, when he was very competent, very good, he typed very fast. And he typed so fast that they never tested it with typing so fast. And that gave concurrency bug, and the dose of irradiation was multiplied by like 1,000 or something. So people die because of these bugs, okay? And now with cars, with the Orlyval, Metro automated things, bugs here, they kill people. So it's kind of funny, huh? We have deterministic data flow, which is really simple and everything, and easy to prove and correct, and no bugs. It's functional, but it doesn't work in the real world. But what we want is a system in the real world, like metro or car or lift control system. But once we go to the real world, it's much harder, and we introduce lots of bugs. So all the nice bug-free programs, it becomes very buggy all of a sudden and dangerous. So it's funny, huh? Going to the real world all of a sudden makes the programs much harder to write. And so that's why it's important to follow something like this. So I'm going to follow this, and you'll see how we do it. You can even do more rigorous than this. Huh? So I start from informal specification. So first we have to know in our heads. This is very straightforward, what is going on. Then we define what are the components in your system. And the components are talking to each other. So we define what are the message protocols. And then each component will be an agent with internal state. And it has a state diagram. So we have to define the state diagrams. And I will show you all of that. So the hard part is these state diagrams, okay? Really getting them right. And this is still not code. This is pictures, okay? What I like to do is define them by drawing pictures. And you have tools that let you define state diagrams. And at the very end, you write the code. So you do almost everything without writing any code. And then you write the code, and you test it. And all kinds of corner cases, fast and slow and everything. But that's not good enough. You also have to prove properties. And there's different ways to do this. There's courses on this. So there's Charlotte Pescher, his course on concurrent programming, does this kind of thing, verification. There's techniques called model checking that let you verify this. So I can do a whole course on this, but I'm just going to touch on it. But this is very important, also. You have to do both. So there's three pillars, You have to do a rigorous design, you have to test it a lot, and verify. Three pillars. If you miss one of those, you're dead, okay? You will certainly have bugs. And even if you do all three, you have bugs. Okay, so this is what we're going to do for the example. Okay, one important thing is that the agents have internal state. They are state machines. So any running program is a state machine. Whenever the program changes the value of a variable, it's a state change. But here, the state machine is really the heart. And so we're going to have a notation of state machines. And so the states will be these circles. And we will have state transition. And the way it works is first you enumerate what are all the possible states. There are all these balls here, all the possible states that the system can have, and the messages that it can receive. So the component here has all these states, and messages come in. Okay? And whenever a message arrives, the system can change state. It might change state in some way. And so we have a notation for that. Okay, so there's many, this is a very widely used idea. It's called a finite state automaton. Okay, but the notation I give you here is going to be really good for multi-agent. So when I'm here in the first state, I have this arrow, and I have something written on the arrow with a slash here. So I receive a message. I receive the message, and that causes the transition. I can also add Boolean condition. It's not always going to do this. Depending on whether the condition is true, this is the condition to make the state transition. And on the right-hand side of the slash is the actions, what I do. So maybe I send another message. Maybe the agent will also send a message. So there's a send message here. And there might be some other action, okay? Real world action. Like in the lift control system, the lifts have motors making go up and down, or opening the doors, closing the doors. So this could be a real-world action, okay? The state transitions then are annotated with this thing with two parts. The left is the condition and the right is the action, okay? And the whole collection of all of these is called the finite state automaton, and that's what we're going to design. We're not going to write code in the beginning, okay? And after we make the whole state diagram, then we write the code, okay? So the code, people love to write code, but here the code is done at the very, very end. Most of the work is without code. It's thinking about state diagrams and reasoning about them. Okay? Okay, so that gives you the idea, the methodology. Now we're going to apply to lift control system, and we'll go from beginning to end. So you're really going to see the whole thing with all of the dirty code that comes out of it. Okay? This is actually fairly realistic. It's actually similar to real lifts in hotels and apartment buildings. So usually apartment buildings, it's very simple. You have only one lift shaft going up and down. But maybe you can press buttons. And lifts can be smart or stupid. So for example, the lift in the Department of Computing Science is very stupid, okay? That means if you click on a button, you will go there. But if you want to go to another place, you have to first go to the first thing you clicked on and then go to the second thing. And so it's kind of a dumb lift. What I'm going to show you here, you can actually make it dumb or make it smarter. I'll show you how to make the code. You can put in some smart components or not. You'll see how to make it smart. In a hotel, usually there's many lifts. Like I mentioned before, so I go to lots of conferences and they have these big hotels with 30 floors, and usually there's like 4 or 6 lift shafts, piles of buttons all over the place. Okay, so when I click the button and I want to go to some floor, one of the lifts will come. Which one? I don't know. So the lift control system decides which one comes. Maybe there's already one here and it just opens the door, or maybe not. So if it's smart, it picks one that's close by, okay? Or it picks one that's already coming down. But if it's stupid, it picks a random one, and maybe the random one is at the 30th floor and is going up, okay? So you see there's a lot of possibility to make it smart or dumb, or buggy also. I'll start with the informal specification. I'm already starting with it, I'm already telling you the kind of thing it's doing. Overview of the system and how it's embedded in the real world, who presses the buttons. And we're going to identify which are the components and their message protocols. In this case, the message protocols are actually simple, okay? But you can add complicated ones. I'll show you some example of that. We're going to have 3 components that need the state diagrams. We'll design them: controller, floor, and lift. We'll start with the simplest one, which is the controller, and then the floor, and the lift is actually a pretty complicated state diagram. How do you make it right? I'll kind of show you how to make it correct. And then we write the code. And I'll show you the running code, and hopefully it works, okay? We can try it in lots of scenarios, pressing buttons, but that's not good enough. We also try reasoning. So you look at the state diagram, and you reason. If I press a button, will the lift come? So there's a state change. Can you prove that the lift will eventually come? It's not so easy, because anybody can press buttons all the time. People can be pressing buttons and it has to work, okay? And all the lifts are moving at the same time. It's completely concurrent. Probably you've never written such a complicated concurrent programming in your life, okay? I don't know if you have much experience with concurrent programs, but this is, every agent is concurrent. And it's we wrote concurrent programs in deterministic data flow. We made digital logic. Remember the adder, the digital adders? With 64-bit adder, it uses like several hundred threads. So you have written a program with hundreds of threads. But deterministic data flow programs are very easy. They're just functional. So they're not really hard, so it's not really very impressive to have 400 threads in deterministic data flow. It's very easy. It's much more impressive to have 20 threads in one of these programs, okay? Because here it's all non-deterministic. So this is probably the hardest concurrent program that you've seen, which we wrote to write. And this is not even a very hard one. In a factory, you can have hundreds of machines that are doing product lines. So you have these product lines where the partial products are moving on transport networks from one machine to another, and the robots are doing stuff. That's quite complex, okay? And it takes a lot of expertise to write those programs. It's really a special expertise, okay? So here's a diagram of the lift. We have lift shafts. So each lift goes up and down in like a vertical tube, which is called the lift shaft. And you have a number of floors, so they're orthogonal. Each floor will connect with each lift. And then you have users, which are the humans, okay? So the users are also modeled. They're component instances. The users are also modeled. They also have behaviors and everything. It's just we're not going to write the code for the users. The code is already written for these guys. We're only going to write the code for the lift, okay? So what happens here? You have lifts, you have floors, but you have a third thing. Because the lifts are controlled by motors going up and down with cables. And those motors are not in the lift. They're very heavy-duty things. They will be outside. They will be either in the basement, or sometimes they're on the roof, okay? They could be on the roof, but there's one controller for every lift shaft. So if you look carefully at a real lift system, you will notice that there is a controller somewhere. It's either in the basement or on the roof or in the high up. And this one will make the lift go up and down. Now, each floor has a button to call the lift, and the lift internally has also many buttons to go to different floors. I want to go to floor 1, 2, 3, up to 30. So there's many buttons, and any of those buttons can be pressed anytime. So that's basically the situation. So this is all informal specification. So now we've kind of identified the components. So there's actually 4 kinds of components. The users, the floors, the controllers, and the lifts. Okay? So that's nice. But now we have to look at what are the protocols between these components. Okay? So here's basically a summary. The protocols here are actually quite simple. But you can make them more complicated. I'll show you a more complicated example at the end. But here it's very simple. So the human user can press the button. He's sitting on floor 10. He wants to call a lift. So he presses the call button. So that sends a call message to this floor component. And the user can also be inside of a lift, physically inside, and go to a certain floor. So basically sending a message to the lift saying, I want to go to floor F. So when the user presses a button inside the lift, it's a call F message going to the lift, okay? Now, the floor can also send call F messages because the floor can call the lift to come to me. So the floor will also send call F messages to call the lift. And then there's more messages. So the floor calls the lift, and this is a protocol actually. Eventually a lift comes, and when the lift arrives, when it's at the floor, it sends an arrive message to the floor. It says, I've arrived. Usually that can be a mechanical thing. It actually sits mechanically on the floor. And then the floor will do things like open the doors, close the doors. And when the lift is allowed to leave, the floor will send a confirmation back saying, you can go. And I will model this as a one-shot, because that's a single thing. So it's a single, here it's already going to be a single assignment. The acknowledgement says, you can leave now. Okay, so there's actually 3 messages. I call the lift comes, and the lift is allowed to leave. It's allowed to leave. It doesn't mean it actually leaves. So the lift is now free to leave. And the lift also talks to the controller. So the lift knows where it wants to go. Okay, the lift knows that from all the calls and so on. But the controller is the one that makes the lift move. So we're going to model the controller in a simple way here. The controller will only move 1 floor at a time. It will move the lift up 1 floor or down 1 floor. Okay? So if you want to go up 5 floors, you have to send 5 messages to the controller. This is for making the code a little bit simpler. You could say go many floors, but then it's harder because what if you want to stop while you're going up, okay? So somehow the lift has to tell each floor when it's there, even when it's going from 10 to 30. Because what if the lift is going from 10 to 30 and somebody is at floor 20 and calls the lift? While it's going up, it should stop there, right? And let the guy in. So the controller in this example is going to be 1 floor at a time. And so the lift says, I want to go to floor D, so I'm at floor F now, or something. The controller knows the floor that I'm at. Maybe I'm at floor 10, I want to go to floor 30, and the controller will move either up 1 floor or down 1 floor. And once the lift is 1 floor higher, like floor 11, it will say at 11. It will send a message back. So this is 1 step message and 1 at message. And if I want to keep, and then the lift, it's at floor 11, but it still wants to go to floor 30, so it sends another step message. I want to keep going higher, okay? And at. Now, you can even make the lift control here very smart. You know, real lifts, they don't have an undo, if you notice. I want to go to floor 30, but that was a mistake. I pressed it by accident. Well, I have never seen a lift where you could undo that. But you could make a lift where you undo that, where you can, well, it no longer goes to floor 30, okay? Strange, huh? You could improve the performance, but somehow there's a standard way of doing lifts, and people do it like that for many years, okay? Okay, so that's the component. Now we have to make the state diagrams, and this is a little bit harder. And I will make the state diagrams on the board, because it's like programming, okay? It's the real hard part is making the state diagrams. So I'm going to make them with you piece by piece, so you see how to do them, okay? And this is where you have to actually do the thinking. So it's not writing the code. The code is easy once you have state diagrams. We're going to start with the simplest state diagram, which is the controller. So here it is, but I'm going to leave this slide here, but I'm going to show you how to design it. Okay? So the controller. So first you enumerate the states, and you have to understand what's in the states. So the controller has basically 2 states. It's stopped or it's moving, running. Okay, the lift is moving or it's not moving. Also, it knows what floor it's at. So if it's at floor 10, it's F. And then it starts running until it gets to floor 11, and then the F becomes 11, okay? And also, each controller has a lift ID, LID here. It knows its own lift, so I'll put that in the state. So you have everything there, okay? So you have stopped state. I'm stopped at floor F, and my lift is LID, and I have another state where the motor is running, okay? And it's coming from floor F, and it's the same lift. Now, in order to make this really work, I have to attach it to an electric motor, okay? I have to somehow interface the controller to an actual electric motor sitting in the basement, okay? So in my simulation, I'm not going to do that. I don't have an electric motor here. Actually, it would be nice to have a real example because we have cards that could do that, little controller cards. But now I just want to do simulation. So what I'm going to do is I'm going to have a timer. What I'm going to do is I'm going to define a timer component, which is going to be like modeling the electric motor, okay? And I'm going to send a start timer message. So the timer component, it's just so that I don't have to do real motors, okay? I will do start timer, and it eventually sends a message back called stop timer. Okay, so this is for my simulation. In the real system, this would be an electric motor, okay? Okay, so what happens? So now we have to design all of the state transitions, okay? And with the notation I showed you. And so, for example, we're here. It stopped at floor F. It receives a step message. Remember, this is a notation with the slash, right? It receives a step message, and F is equal to the floor it wants to go to, the destination. Well, that means we don't have to do anything, okay? So this is a little loop back here, and the action is nothing, okay? So in the case when I do a step, and I'm already at the floor, I do nothing, okay? But now I can have another possibility. I receive a step message, and F is different from the destination. Now I have to start the motor running. So I send a start timer message to the timer. Let's say there's a timer ID here, and the controller ID here, because the timer has to send a message back to the controller, and there's some time. Let's say 5,000 milliseconds, okay? 5 seconds for our simulation. We let 5 seconds. But we will be going to another floor. So the state will change. So we have to compute the new state. So I'm going to do it like this. New F. If F is less than destination, then I have to go up. So if I have to go to floor 30, I'm at floor 10, then the new one will be F plus 1. Otherwise it's F minus 1, okay? So the new F here will either be this old F plus 1 or minus 1, okay? If it goes up 1. So then I'm in this state, and I stay here until something happens that I change. Eventually I'm going to receive a stop timer message after 5 seconds. So you see there's time here, huh? This is not just some mathematical thing. This is in the real world. There's a time aspect here, huh? So after 5 seconds, I will receive a stop timer message. I remember the left side of the slash. And then I will send an at message, at F, to the lift ID. Like we said before in the diagram, the protocols, and I go back to stopped. And that's it. And I'm here again. That's the whole state diagram, okay? Notice it obeys this idea. I do a step, and an add message comes back. So the controller state diagram, this is the full controller state diagram. You see that? How it works? That's pretty easy, right? Now this one was a little bit tricky because of the timer, because we're doing a simulation, okay? This whole program, so I'm going to show you the running code, and it'll be a simulation, and it will be doing things at certain times. So it's running through time, huh? And so this timer is very important. And this 5 seconds is very important because it kind of organizes the simulation, huh? Okay? So this is my controller state diagram. Let me show you real quickly now what the code would look like for this. So I'm not going to run it yet. Huh? Let me just show you the code here. So here's the controller. See if I can make it a little bit bigger. Is that readable? So this would be the code for that state diagram. And this code is automatically generated. Once you have the state diagram here, that's everything, yeah? You can generate the code with some tool. You don't actually have to write the code if you have a smart tool. There are tools for doing this, huh? Industrial tools. So this will generate the code. So here I have the timer. So the timer is a port object with no internal state, up here. It receives a message, start timer. It creates a thread. It delays T, and then it sends stop timer back. So it does exactly what I showed there. And here's the code for the actual controller. Here I have the new, it's a port object, so it has a state transition function. Okay, and this is the function. And the state, here, there's actually a syntactic convenience. The state is always going to be a tuple. So I'm going to model it as a tuple with 3 elements. So motor, F, and LID, and then message. So this is the state transition function. It takes the state here and the message. So this already does a case statement. This notation where I put the tuple inside the header here is just making the code a little bit shorter. It actually already has a case statement here. So here now I have the actual code, and it's always 2 nested cases. I have to do a case on the state and a case on the messages. Here I have case motor, running, stopped. And then when I'm running, I wait for a stop timer. When I receive the stop timer, I send a lift ID, and the new state, so this is the result of the function, is going to be stopped FLID. Okay, and here the stopped, in the case of when I receive when I'm stopped, if I receive a step message, if F is equal to destination, then I'm done, I do nothing, huh? I return stopped FLID. Otherwise, if F is less than the destination, I send a start timer. Here it's 1 second, huh? Because I'm going to show you the simulation, so every second something's going to happen. And then the new state will be running F plus 1 LID. And in the case where F is greater than the destination, I send, again, I start the timer, and the state will be F minus 1. And that's it. So that's the code for this state. Okay? But this is the simplest one. Okay? The other ones are harder. But maybe this is a good time to make a small break, since the other state diagrams, this is the easiest one. It will be a little bit harder than this. So I make a break, and then we will do the floor and the lift. Okay? And then we will do the code, and we actually run the beast. Okay? So before the break, we did the controller state diagram. So now we have to do the floor and the lift. But the floor, let me do it completely from scratch. So how does a floor work? We have to think how a floor works. Well, when the floor is doing nothing, nobody's calling it, it's sitting there minding its own business, and let's say put it in a state, let's call it not called. So nobody is going to that floor is not calling a lift, okay? But then somebody comes and upsets the poor floor, it's just minding its own business, and presses the button. Well, then the floor has to call a lift, okay? Let me go here. So there's a state transition. Let me write later what it does on this. So the floor can go into the state where it's waiting for a lift to come, for some reason, okay? Somebody pressed a button. And then the lift actually arrives. Well, the floor had to actually do work then. It has to open the doors, because the floor is controlling the doors, okay? So there's another state. Let me call this one doors open. Eventually it goes there. Doors open. But the doors don't stay open forever. Eventually the doors close, and the floor is back to, and the lift goes away, or whatever, and the floor is back there. So the life cycle of a floor, you have this cycle, okay? It's not called, it's calling a lift. The lift arrives, the door is open, and when the doors close again, the lift goes away and it goes back to non-called. Okay. But this is only the framework. Now we have to look at the messages. Okay? So what are the possible messages? Well, we actually thought about that already. Okay. Here we have the floor, a call message. When somebody calls it, it will call, presses call, it will call a lift. And the lift arrives, and the lift can leave. So we have to take care of these messages. Basically the call message and the arrive message. Okay? Okay? So there's a call message here that's coming. It's not called, call message. So what does it do? So this is the receive part, on the right here. What does it have to do now? So it will transit to the called state, but what does it do here? You can see it there. It has to send a message to a lift up. And the floor has actually a number which doesn't change. Let's put the number here. There's a number which doesn't change. It's like a constant, this floor. So it has to send call F to some lift. Which lift does it send the call message to? Not to all of them, because if all of them come, well, maybe if it's really dumb, it sends to all of them. And then when one lift comes, the user goes in and leaves, the other lift comes for no reason. Okay, fine. But, so basically, let's just say it sends to one lift. Let's make it really, really stupid. Some random. It picks a random lift ID out of the 6 or how many there are, and sends call F message there. Okay, and then it comes in this state. And what happens then? Well, eventually the lift arrives, So we have this arrive message coming here. Arrive. With some acknowledgement. This is telling me that I can go, actually, yeah? And now I go to this state. But now, actually, if you think about it, in our simulation, we need another timer, right? Because the doors open and the doors close. There's another electric motor there managing the doors. So there's actually also a timer here, right? So we send start timer. Some time, whatever. Floor ID to the timer. Okay. So this models that the doors open for 5 seconds. And eventually, I have a stop timer. Message arriving. And the doors close again and I go back to not called. But when the doors close, I have to tell the lift that it's okay to leave. Okay, so I bind ack to some constant. Let's say okay. It's a little constant saying you can go now, and the lift knows it's free to go. Okay, so that's the basic cycle of it, right? What do you think? That's the basic framework of a floor. But we're not done, We're by far not done. Because there's a principle that we have to follow. All messages must be accepted in all states. So here we do a call button. But if you're like me or many people, if the lift is not coming fast, you will press many times that call button, And so the floor will receive many call messages. It will receive a call message here. So what do we do? What happens if it gets a call message here? Well, basically nothing, because it's already calling a lift. But you have to handle it, you see? You have to put in something like this. Also, when the doors are open, you can get a call message, but nothing is needed there. That's pretty stupid. Yeah, call lift and the door is open. Okay, but it can happen. You have to handle it. And if you don't handle it, then the code has some kind of a bug, a deadlock. Huh? If these call messages will not go away, okay, what happens to the call messages? So the call messages will stick around until they're taken by the agent. Huh? So you have to swallow them, these call messages. Huh? So the call messages are handled now. Are we done? What do you think? It's over? We have a full, is this the full state now? Is there anything missing or not? What do you think? Without looking at the slides. Is everything done here? Well, let's take a look at this principle. All messages must accept in all states. So the floor accepts another message, not just call, huh? Which one? Which one does it accept? Not just call, but there's another message coming to the floor, huh?
The lift arriving?
Arriving, yeah. So the arriving is here. Now, is it possible to have an arrive here, arrive coming, or here? If the floor is not called, could a lift arrive there? Of course. Someone in a lift somewhere might want to go to that floor. So a lift can arrive at a floor even if it's not called by the floor. So you need to have arrive here, and there's another value. Now, in fact, to be very smart, you have to manage all of these acknowledgements, but I'll make it very simple. So we'll just bind them all together. So all the lifts arriving will leave at the same time. Okay. But in fact, in real lift system, you have to handle each lift, because each lift will have its own door. But let's just, for simplicity, say that when this guy is allowed to leave, this one also. Okay. What about when the doors are open? Is it possible to have an arrive message here? What do you think? Have you ever been in a hotel with many lifts? Of course there can be. If I have a lift opening, there's a lift right next to it, someone coming down and it opens. Of course it can come up. So of course I can have an arrive message coming here, but the doors will stay open. Let's just make this very simple. In fact, to be really correct, every lift has its own door that opens. But we'll just say it's a general doors open thing to keep our code simple. Okay. Is it completely correct now? Everything is fine? Yeah, technically we have to reset the timer and stuff, but let's just keep it simple. Okay. So am I good here? This is actually the other side of the slash. Huh? Am I good here? There's still something missing, huh? Right? What's missing here? There's still something missing, right? There is something missing, huh? What's missing? Something's wrong here. This is a buggy floor. Well, the door's open for 5 seconds, right? When I go from called to doors open, I start the timer, they open, and then they stop. But when I go from not called to doors open, I have to start the timer too, right? So I also need to do start timer here, huh? Whatever, as before, huh? Because the timer is not going to start by itself, huh? It only starts when I send it. So whenever I go into doors open from another state, I have to start the timer, huh? And then the timer will stop here. What about this one? Does this one have to start the timer? No, it's already started, huh? When I'm in doors open, the timer is already running. Unless you want to be very smart and reset the timer, because otherwise the rift might come and there's only 50 milliseconds left, and you know, it will only open, but we'll keep it simple. So technically you would have to reset the timer here. You can do that as an exercise. So now we're good, right? How do we know we're good? Well, we have followed this rule. Okay. We have followed other rules, that there is also that always the timer start when windows open. There's a stop timer message here. We always tell the lift, the act is when we stop the timer, we tell the lift to leave it to go. So we're correctly following this protocol. So the protocol seems to be correct. So this seems to be reasonable, right? This is the floor state diagram. It's kind of dumb because we picked a random lift. You could be smarter here. I'll show you a little later if we have time that you can do this much smarter. Okay. Okay. So that's so here's the controller. This is the one in the slides. It's about, I think it's similar, huh? This one is supposedly correct. Okay. Now the final one, which is the lift state diagram. This is a toughie. This is the hardest one because the lift has a real memory. If people in the lift click on 1, 5, 10, 15, the lift has to remember that it has to go to 4 floors. And if somebody calls it, it has to remember again. So it needs to remember a sequence of floors that it has to go to. The state of the lift is much more involved than the state of a floor. A floor doesn't have to remember very much, huh? But the lift actually has to remember a whole sequence of floors that it has to go to. If it doesn't, there are very stupid lift systems that don't do that, huh? Sometimes you see that in apartment buildings. You click on floor 5, and then you cannot click on anything else until the lift actually arrives in floor 5, because it only can remember one number. I have actually seen very dumb lifts like that, but this lift is smarter. This one will remember the whole sequence, okay? So let's start designing it, okay? I'm not going to design it all from scratch, because that would take too long, but start designing it. There's actually loops in there. The lift has to do iterations, because two nested loops actually has to do. Okay, so let me see just to make sure. So there's there's actually a schedule, which is the list of floors it goes to. So the lift has let me call it a schedule. It has also a moving flag, which starts by, in the very naive case, the lift is doing nothing, okay? It also has to know a controller. Let me just make sure I'm not too inconsistent. And it's at a particular floor, position. So this is the lift when it's doing nothing. It's sitting at some floor. It has to go nowhere. So schedule will be a list of floors that it goes to. And moving will be whether it's moving or not. So an idle lift looks just like that. But there's a way of making the lift not idle, huh? There's actually several ways of making the lift not idle. Somebody has to call it. So it has to actually be called to a certain floor. Let me go back to here. So the lift will accept call F messages to go to floor F. Okay? And once it has a call F, it will add that to the schedule. Okay? So there's another state here. It's at a position. And the schedule is different from nil. For example, it has a call F And here somehow I have to add F to the schedule, okay? Let me just do it like this for now. And it's moving now. If the schedule is nil, it has to be doing, it has to be active, so it's moving, okay? And what does it have to do? Well, it has to send a step message to the controller, okay? Has to send a step to whatever destination it goes, which will be the F, huh? Let's say, this is a list, so let's say the first element of schedule to the controller. So you see it starts getting more and more complicated, huh? But let me show you the diagram, and I will explain how it works. So here is the lift state diagram, and you can see it's not so simple. Okay, so here is the base case. The lift is sitting on the floor. It has to go nowhere, and it's not moving. And I call it to go to floor N. If N is different from where I am, so this is important, then I have a new schedule, which is a list containing N. And I send step N to the controller, and I move here to this state. Okay? Moving is true. And if I arrive at N, I go down here. Now the lift also has to do something with the doors. The lift arrives, and it's the floor that's controlling the doors. Okay? But the lift is like attached to the floor when it arrives. So the lift is not allowed to move as long as it's attached to the doors. If it tries to move, that's kind of it will break, it's kind of a bug. So it has to wait for the doors. That means it has to wait for the doors to close, and it's not connected to the doors anymore. That means when it arrives at N, a position, and the position is the first element of the scheduler, then it's here, it goes to wait for doors, it sends the acknowledgement message to the floor. So that's the other side of the protocol. It sends it to the floor, and it waits. It waits until the acknowledgement is bound. If there's nothing more to do, if schedule.to is nil, that means there's nothing more to do, then it goes back to the idle state. Right? And the new position will be N pos, this new position, and the new schedule is nil again. So there's a basic loop here also, like this, But it's actually much more can happen, unfortunately. Okay? So I can get many call N messages anywhere. Now, to simplify a little bit, the call N messages, I will only accept them in the two main states here. Okay? Not when I'm waiting for the doors. Because waiting for the doors is a temporary. It's a temporary state that has a short time duration, and I cannot move anyway while I'm waiting for the doors, so I don't really have to handle the call N message here, because after some time I will always go back to one of these two states. Okay? So the call N messages are handled in these two states when I'm not waiting for the doors. So here's a call N when N is different from the position. Here's a call N when N is equal to the position. So if the lift is there at my floor and I'm calling it, oh, it just has to open the door. So it's this state here. It sends the arrive to the floor immediately, and it waits for the door. So if the lift is already there, it can just open the doors and then wait to leave. Okay, so that's a simple condition, if the lift is already there. And if the lift is not there, okay, so N is different from the position, I send a step to the controller, and the controller will send an at message back. Okay, now this is actually a while loop. if the at coming back is different from schedule.1, that means I have to send another step to the controller and go back. So this thing is like a while loop. It will keep circling until npos equals schedule.1. You see that? So this together with this is like a while loop. See how it works? If I arrive at some floor, but it's not where I want to be, I send another message to the controller, and then I arrive again. If it's not where I want, as long as I'm not where I want to be, I will keep reactivating the controller until I'm where I want to be. npos equals schedule.1. Okay? So these two together is a while loop. Okay? But there's another while loop. There's actually two nested while loops. So let's say I'm here, I call n. The new schedule is n. I have to go to floor n. But now I'm moving to n. But while I'm moving, someone sends another call n. This is a different n, going to a different floor. And I add n to the schedule. So I have some function. This list, sched is a list, It's the list of floors I go to, but I put it at the end. So my naive protocol is, if I go to floors 1, 5, and 10, and if I add 15, I just put it at the end. That means I always go to 1, 5, and 10 first, and then to the next one. So my naive protocol is that anytime a new call message comes, I stick it at the end. I have this function schedule last, which basically adds n to the end of the list. And then I come back here. So schedule is updated. But meanwhile, this loop is still running. When I arrive at schedule.1, I come here. I wait for the doors. When I'm allowed to leave, let's say I'm allowed to leave, but schedule.2 is different from nil. That means there's still more floors. It's not the only floor. There's still more floors. So I basically... The new schedule is the rest. It's schedule.2. It's everything except the first. And again, I reactivate the controller. See that? So this thing, these two here basically, the condition is schedule.2 is nil or different from nil. These two is another while loop. There's two while loops running here, kind of at the same time. So while this one is running, going to a floor, I can add more floors to it, and whenever I arrive at a floor, I will add, if I'm not done, schedule.2 different from nil, I will set the new schedule, schedule.2, and I start again, going to the next floor. So it's like two nested while loops. See how that's working? And the way to make it is you have to follow the principle. We have to follow all the protocols, and all the call messages have to come in at the right time. Okay? So the call n, you can have many call n's, and you add them to the schedule. Okay? Now, these two here are another while, are the main while loop, the big one. As long as schedule 2 is different from nil, it's still moving, okay, and looking for the floor. But once schedule.2 becomes equal to nil, then I'm done, and it goes back to the idle state, okay? But maybe it never goes to the idle state, It can stay here forever. If people are always pressing call ends, then this loop will, whenever the lift arrives, the schedule decreases. You see that? But whenever someone presses a call, the schedule increases. So both of those things can happen. So the schedule is like moving out. It's decreasing whenever I arrive at a floor, but whenever someone calls, it's increasing again. Okay? And maybe it goes all the way to nil. If people stop calling the lift, it will eventually exhaust itself. But if people keep calling, it will grow and grow. Can it grow forever? Could it become infinitely long? What do you think? No, why not?
I mean, because there's a limited amount of floors.
Because there's limited amount of floors. So schedule the last here, if n is already in the schedule, it's not going to add n, okay? So the maximum size of the schedule is just all the floors. So there's no problem with memory. But you see, you have to think about it, huh? You have to think, get that? If it would be totally naive, if we just add without checking, then this list could grow, but we're not that naive. We first check whether n is already in the schedule. So the maximum is going to all floors, and that's it, no more. So that you can stay forever then in this place. If there's many people, it's a very busy hotel, people are always pressing buttons, but in the middle of the night, people eventually go to sleep, and the lift becomes idle, and it goes here. Okay. You could even add a protocol where the lift goes back to the ground floor. Here it stops at any floor. Okay, which is actually the behavior in the lift in computer science. If the lift is at floor 2 and nobody does anything, it just stays there. But in hotels, they usually don't like that. So in the middle of the night, all the lifts come back down to the ground floor. So there could be a thing here that makes this lift, as long as pos is different from 0, it could be moved down to the ground floor. So you could add states for that. You see that? How it's working? So this is not so simple, huh? What do you think of that? So this is the state diagram for the lift. Each lift is running this. Okay. But maybe we want to see the code running, right? Okay, so let's look at the code. So I have to start Mozart again, but first run show you the code here. So here's the controller. Here's the floor. You can barely see it, the whole thing. Not called and called. So there's again a new port object, a function, which is the state transition, 2 nested cases. So you have the top level is the state called, not called, and doors open. And inside there's a second case on the message arriving. So there's always 2 nested cases, which is on the state and on the message. You could flip them up. You could actually first do case on message, and inside there do case on the state. It depends on what your preference. So you see, you could actually write it in a different way. You have actually 2 things that are determining the action, the state and the message. So if the message is call, I put in a browser so we can see the simulation. I pick a random lift. So lifts is actually a tuple which contains all the lift IDs. 1 plus os.rand mod with lifts. So this will give me a random lift. Okay? Using the os.rand. Random, this could be a random integer. And to that random lift I will send a call. Okay? So I'm doing exactly what I'm doing in the state diagram here. So this code actually is very faithful. The time is a little bit different. So if I'm called and the lift arrives, then I will send start timer message. Okay? If the doors are open and I get a stop timer message, then I will say here I say equal unit. Unit is just a constant. Is a constant that I use when I don't want to give a name to the constant. It's just some particular constant. You know that true and false are constants, and there's 2 of them. Well, there's also a single constant called unit, but this could be okay. And then the state goes back to not called. If a lift arrives while I'm door open, I will merge the 2 acknowledgements so that I will let all the lifts leave at the same time. This is kind of a simplification. What you really want to do is keep a tuple of x and I have a separate timer for each one, but that makes the code more complicated. And in this example is maybe too much, okay? So that's the floor. So you see this code is very straightforward. It looks kind of complicated, but actually it's just this, okay? So you can see that the way to write multi-agent system is to do this, okay? State diagram, and not to do the right code first, which is a very bad idea, okay? This is also much better than linear code. Okay, now let me show you the lift, and then we try running the stuff. So here's the beginning of it. So I have this schedule last function. Okay. Oh, maybe it's not good enough. Oh. If L is different from nil, and the last element is equal to n, then I just return L. But maybe what I should be doing is checking whether n is a member of L. Huh? Oh, I'm not doing that. But you have to prove that this is enough. That you cannot bring in an n in the middle. Can you? Maybe you can. Who knows? And otherwise I append n to the end here. And here is the lift. The lift knows about all the floors, so it has a tuple floors. Again, there's a state transition function. It has the message call at. Is that the only thing? Yes. Okay. This is actually, look at that. It fits in one screen. It's not that much code, even though the state looks more complicated. Because of the list, it's easy to manage the list. So if I'm at a position, I look at the scheduler. If the schedule is S schedule 2, so if I'm at a position, I take S. If I'm at S, I send an arrive message, and I wait for the thing to come back. Here I'm using a syntactic trick of Oz, where this arrive variable is actually an argument to wait. Okay, this should be actually 2 lines. So I send arrive to the floor, and then I wait. And if schedule 2 is nil, then I go back to an idle state. Otherwise, I'm going back to, I'm still in a moving state. The new schedule is schedule 2. So this is actually not so much code, even though the state diagram looks a little bit more complicated. Okay? And now I want to actually run the simulator. So I've defined a procedure called building, which creates a building with Fn floors and Ln lifts, and returns these 2 tuples. Okay? So lifts, I create a tuple of n Ln elements. I create, for each element, I in 1 to Ln, I create a controller, and I create a lift, okay? Lifts.I. And for the floors, I create a tuple, and for each n there, I create a floor. And notice that lifts and floors is an argument to lifts, so the lift knows all the floors. And lifts is an argument to floors, so the floors know all the lifts. So this creates building, and then we can do some experiments with this. Okay, so I'll run it. So here's some things. So for example, I create a building with 10 floors and 2 lifts. Floor 9 does a call. Floor 5 does a call. Okay. Lift 1, I'm standing inside lift 1, and I want to go to floor 4, I can call 4. I'm inside lift 2, and I want to go to floor 1. And then you'll see how the thing is running, okay? So let me run this whole business here. But let me take these, let me make it so it's one piece of code. So I need a new port object abstraction. copy this whole thing into the browser. Oh, wonderful. Okay, I have to do it again. Okay, copy. I have to start again. Okay, here's the Mozart system. Paste. So this is the whole code. Let me now do a feed buffer. Okay, it's accepted now. Now let's write doing some stuff. Let me copy this code here just to make things simple. No, that's not what I need to do here. Paste. So I'll create a building. Call it. Now I needed a lift at floor 9, so you see what it's doing, huh? Okay, 9, open doors, close doors, and I'm done. It's nice, huh? But I can do more stuff, of course. So I can go to many places. So here's a bunch of things. So floor 5 is calling a lift. Lift 1 wants to go to 4. Lift 2 wants to go to 1. The floor 10 is calling a lift. Five. Okay. So you can verify that all the right stuff is happening, right? 10, needed a lift, close doors, and I'm done. If I do something else, maybe I need floor 1 needs a lift, and floor 2 as well. Two goes to floor 1, and then goes to floor 2. Oh, that's kind of dumb, huh? Well, both of these calls sent to the same lift, lift 2, but somehow this one went first. So the lift is first going all the way down to 1, and then it goes back up to 2. A smarter one would have actually opened at 2, right? So the schedule last function can be made smarter, actually, yeah? And let me now show you another kind of protocol to make this thing smarter. So we can add all kinds of protocol to make it smart, depending on how much time and effort we want to do, and this lift control system. So let's say we want to do, this is called a negotiation protocol. Let's say I have a floor here, and I have lift L1, L2 to L30. And these are at different floors. Maybe this one is at floor 5. 30 is a lot of lifts. That's 6 lifts. This one is at floor 30. This one is at floor 21. So there's 30 floors, let's say, yeah? And this is floor 4. This one is at floor 5 going up. This is 30 going down. L3 is at floor 3 going up. Okay? So they all have different states. Now, the way it currently does is that when I call a lift at floor 4, I send a message to a random lift. But in fact, I can do better than that. I can do a negotiation protocol. What I do is, I send a message to each lift saying, where are you? To each lift. The lift will send a reply back. So this one is at floor 5 going down, etc. It sends a reply back. And then, when this floor receives all the replies, it picks the best one. So the best one will be maybe lift 3, yeah? It will say pick lift 3, and then it will send a message to lift 3, call 4. Okay? This is an example of a negotiation protocol. Okay? The same kind of protocol you can do, it's actually done on the web, you can do it. If I want to get an airplane ticket, for example, you have these, I'm not sure what it's called, these collector sites. I say I want to go from Brussels to Oslo, Norway, and they will send messages to all the airlines, and they will get the prices, and they will tell me which is the best. So they're doing something like this. This is a kind of negotiation protocol, and you could extend the lift control system to do this. You see that, huh? Which is kind of neat, huh? To make it kind of smarter. Another way of making it smarter is that the lift will, yeah? No question? So let's say the lift is going up from 1 to 30, and it's at floor 5. Okay, going to 30. And then once at 30 it goes down. Okay? But once I'm at floor 5, let's say I want to go to floor 6. The naive protocol will go all the way up to 30 and then down to 6, which is kind of stupid since 6 is on the way. So the smart protocol would see whether the floor is on the way and would insert it in the middle of the schedule. This is actually the protocol that's used for disks, magnetic disks, because the disks have a head, have a disk ahead. So this is a disk that's turning. People still use these things, even though there's SSDs. You have a head that moves back and forth and reads the tracks. You have the concentric circles. But this is a mechanical thing. And if I want to read a sector of the disk, I have to move to that. So it's like an elevator, going to floors. But changing direction for this thing is very expensive, because it's a mechanical device that has inertia. So it's much better that it goes all the way from the outer rim to the inside once, and then back. It sweeps back and forth. And that's what the protocol, that's what disks use as a protocol. If I need to read a sector, it's moving in, I need to read a sector here, it will actually insert that into the schedule. And this is actually called the elevator protocol. Okay? Maybe you know that. It's called the elevator protocol because that's what a smart elevator would do. Okay? But an even smarter one, if you have multiple lift shafts here, like multiple heads, would do some kind of negotiation. Okay? So you see the kind of thing that we can do here. Let me go back to... So we can do tests now. So we have now the state diagrams. Okay? Okay, so we have all these state diagrams. We write the code. We translate them into port objects. So we have 3 kinds of components. Okay? And we can do certain kinds of improvements. We can have, for example, a smarter scheduler. This is what I mentioned, the elevator scheduler. There's another called the 415. Well, it stops at 15 on the way. It will not go all the way up to 30 and then down to 15. So disks use the start center. It's called the elevator algorithm. Okay? Now, So far, we didn't do any verification. We did a little bit of testing. Okay? And you can also verify, reason about the system. For example, the lift will always eventually stop at a floor that is part of the lift's schedule. Okay? How can we prove that? We can prove that by reasoning on the state diagram. Okay? Assume there is something in the floor in the schedule. Some floor is part of schedule. Okay? Well, we can now prove, using the controller property, we have to prove the correctness of the controller, that eventually I will get to schedule.1. We can prove that. So we arrive at schedule.1. And then we can prove that once we do that, we will restart the loop with the rest of the list, schedule.2, until the last schedule is nil. So if we follow the reasoning, we can see that we will eventually get to each floor that is part of the schedule. Okay? Purely reasoning on the state diagram here. And it's independent of all the concurrency. Because the schedule, see, the thing is, the schedule, this list here, is a stable data structure that's not affected by concurrency. I mean, there's only two ways the schedule can be modified. We remove an element from the beginning, and we add an element to the end or somewhere else. Okay? We remove an element from the beginning, and we add some element in the middle. That's the only two ways the scheduler can be updated. And if we notice that the loop is always removing elements from the beginning, we can show that we will always get to every floor. Notice you have to take this function into account. I can build a scheduler that will not satisfy that property if I naively add n to the end here. Sorry, no, if I naively add n. Let's see, how do I do? If I don't go, let's say I go from 1 to 30, okay? Instead of going from 1 to 30, if I always go to the nearest floor, I go from 1, 2, 3, 4, 5, maybe I want to go to floor 6. But then someone presses 5 again. Well, if the protocol is always go to the closest floor, then the lift will always be flipping between maybe 5 and 6, and it will never get to 30, and I will have starvation. You see? So that proof is not completely obvious. It really depends on this function. How do I insert the n in there? Okay? So this kind of reasoning, you have to do it, because if you type the wrong function here, you can have starvation, and maybe if there's too much activity on the lower floors, maybe it will never get to floor 30, okay? But in this case, it will get to floor 30 because all the new requests are put at the end, okay? It's actually behaving like a queue. But if it would behave like a stack, then you would have starvation. Because a stack, the new ones are always put on the top. Okay? You can see that in a supermarket, huh? In a supermarket, when you wait in line, you're waiting in a queue. That means first in, first out. The first person waiting is the first person to be served, and new people come at the end. But if it were a stack, then new people would always go to the front of the line, and the guy in the back would never get served. You see that? So a stack is not a good idea for a supermarket, and not a good idea for this. Okay? So, but this kind of reasoning, you have to do it. Okay? Or if call F is sent to a lift, then the lift will eventually arrive at floor F. So you can prove small theorems like that. Okay? Okay, so now let me kind of give a summary. So you saw this big example now. And it's only the beginning. You can make it smarter, you can add failure handling. You can see multi-agent system is not so easy to do, but you can do it. And there's 3 pieces. So we did today design, and we did a little bit of testing. You have to do more, and a little bit of verification. In a real system, you have to do more, of course. And there is software support for all of this. We've already seen maybe software support for testing, unit testing, and so on. Also model checkers, verification, also tools for helping you design. There's lots of support for this. But you have to do all 3. If you leave out any of the 3, you are living dangerously. Okay? Okay, so that's all I want to say on multi-agent today. So you kind of see how to do it. I gave you a lot of tips and intuition using port objects. How you build large multi-agent systems. Remember, we also showed that deterministic data flow, if you can use it, it's the best. Okay? Flavius Josephus is much easier compactor to write in deterministic data flow than in active objects. But it doesn't work. You can't do that for non-deterministic multi-agent. Like this is an extremely non-deterministic as a lift control system. Okay. So next week we are going to I'm going to present a real live industrial multi-agent language called Erlang, which has a lot of use. A lot of people are using this, and it has another thing that we didn't say today. It is really good in failure handling. It's so strong, nothing can compete with Erlang and how smart it does failure handling. Okay, it's the best system for failures. And in multi-agent system, you will see always failures. Lifts are out of order. The floor is, someone blocks the door and it's open. Okay? Or someone blocks the lift, doesn't move. It has to keep working, the system, of course. So Erlang lets you do that really well. Okay, so let me end there today. So now you can go and do multi-agent. Voilà, c'est tout. Merci beaucoup.